Okay, we'll get going. In these breaks, I can't remember if I told you on Monday, if anything is not clear, that's a great time to come down and quiz me. And then I'll go, oh, yes, I did explain that incorrect. I did give you the wrong number or do something wrong. Or, okay, I'll explain that when we get back from the break a bit clearer. So it's to your advantage if you come down if something isn't clear and get confirmation or get clarification of it. Now, these loads, I said they come from the Australian standards, but where do the Australian standards get them from? Why do you need to know that? You need to know that because you're going to be an engineer, a professional. And it's not enough just to know where to get it from. You've got to understand where it's come from where the book has got that information from. So where do all these loads come from? Well, unfortunately, it's not just as simple as saying it weighs this much or we'll put all that level of live load on. All loads involve uncertainty. So in terms of live loads in a building, okay, you could look at get some observed load densities in office buildings. So we now are going to define our loads as being characteristic loads. We're going to have characteristic dead loads and characteristic live loads because all calculations involve uncertainty, so we are going to use some probability analysis to control this risk, this uncertainty. So we define all our loads as having a 5% chance of being exceeded and we call them characteristic loads. So unfortunately, I'm now going to talk about Bell distribution. You've all done statistics in a very minor way, okay? So we're not going to do a lot of it. Characteristic dead loads. So you may say to me, but Lizzie, we can work out the weight of something. Where is the uncertainty in it? Well, dead loads may vary due to under or overestimated densities of concrete, because concrete does weigh different amounts depending on how much gravel and the constituents you put in there. And dead loads may vary due to materials used on site not being consistent. Or dead loads may vary due to the builder not wearing his glasses that day and reading 100 mil thick as 120 mil thick. So there is always uncertainty in your system. And based on the principles of probability, the accepted practice is to choose a value for the density that only has a 5% chance of being exceeded, and we call this the characteristic dead load. In terms of the live load, particularly with people loading, in the week of a building, you don't expect loads to be high. But in the year of a building, you may say, well, every year in this building, there's the big Christmas gala, and on that Christmas gala, we get hundreds of people in this building. So depending on what time period you're looking at in the life of a building, you may have heard most buildings have a 50-year design life. Okay? They're now slowly increasing that. I think one of the bridges in Brisbane has just been built for a 100-year design life. So the accepted practice is to choose a value of the live load that has a 5% chance of being exceeded once in 50 years. 50 years is chosen because that's the design life of most buildings, but fortunately a lot of old buildings in the city, you know, are older than that. Okay, so it's not to say that at 50 years the buildings suddenly need to be pulled down and don't work anymore. That's just the design life we build them for nowadays. Of course, years ago, they just built them. They didn't have so much statistical analysis involved. But anyway, we call this the characteristic live load. So whenever you're given a live load or a density of concrete, assume it's a characteristic dead load. So what does that characteristic thing mean? Well, it all is based on a standard or normal Bell distribution curve. And just as a bit of revision, we know a normal Bell distribution curve is symmetrical about the mean. And we know the standard deviation indicates the degree of spread. Okay? So in terms of what the standard deviation means here, you'll see 68 as a standard percent of values occur within the mean plus or minus one standard deviation. So that means within this hashed region, you would have 68%, of the data points line. So you would get 16% being over-exceeded and 16% under-exceeded. Now we have to define the characteristic load as the 5% chance of exceedance. Thus, that means there's 90% lying within mean plus or minus 1.65 times the standard deviation and 5% above. So if you have to calculate a characteristic load, when you have a set of data, and you'll be doing that in the practice class next week, you would calculate a mean, a standard deviation, and mean plus 1.65 times the standard deviation would give you the load you are going to apply to your structure. You can't apply an average load. An average load, as I said, would fail 50% of the time. So we have to put an extreme load on there, okay? And that extreme load is 5%. Now, you may be thinking, well, hang on a minute, that means 5% of the time our loads are still being exceeded. So 5% of the time the building might fall down. Is that a good risk? Characteristic loads that have a 5% chance of exceedance, that equates to 1 in 20 chance of exceedance. Would you be happy with that if you were building a building? No. No, so we're not happy with that. So what we do is we get our characteristic load and we then apply load factors to them. We always use the same characteristic loads regardless of what we're designing for, and we apply different load factors. And we call this limit state design. We design right up to the limit. If the yield stress, the maximum amount of stress it can carry is 300, we would do our calculations and ensure we can load it up to as close as 300 as we can. Where our factor of safety lies, it lies in the loading, okay? So we call this limit state design. Our design loads are our load factors times our characteristic loads. So when our limit state design, limit state is a set of performance criteria, strength, deflection, vibration, that must be met when the structure is subject to loads. We don't just design so the building doesn't fall down. You may walk across this floor and I go, assuming it's on the 10th floor of a building, and I'll go, it's perfectly safe, walk across it, and you start walking across it and it starts bouncing. And I go, don't worry about that, it's not going to fall down, okay? You're not happy with that. So we design for deflection, for serviceability, as well as strength. And we put equal weighting on both designs, but the variation comes in our load factors. So limit state design requires the structure to satisfy two principal criteria, what we call ultimate limit state criteria and serviceability limit state criteria. Ultimate limit state criteria is a strength check. That's the failure design. To satisfy the ultimate limit state, the structure must not collapse when subjected to the peak design load for what it has been designed, and that peak design load is 1.2 times whatever the dead load is and 1.5 times whatever the live load is. So we now increase our load from dead plus live to, we increase our dead load by 20% and we increase our live load by 50%. And that is the loading we design to. Now you may think that's very extreme, but the consequence of something failing is people being hurt, okay, is fatalities. So these load factors reduce the chance of the load being exceeded from 1 in 20 to over 1 in 10,000. So now our odds are a bit better, or a lot better. And that is the way we design in Australia. There used to be something called permissible stress design, but I won't go there. Okay, that's our ultimate limit state design. We also design for serviceability limit state design. That is to design so something doesn't deflect too much, so the structure is serviceable. So as well as in that, when you design a sports floor, you have to ensure it doesn't vibrate too much as well. So the limit state that ensures that users are comfortable with the performance deflection of the structure. So we use the same loading, we put different load factors on. So we assume we have the dead load, and now we actually take only 70% of the live load. And what we do is we then say, with that loading, how much does it deflect? Okay, it's less than what it has to be. So there's some upper limit, and we say it's less than what it has to be. So in actual fact here, this increases the chance of the load being exceeded from 1 in 20 to 1 in 5. So you may go, well, what are you doing here, Lizzie? You're putting less load on. But you have to remember that we're starting off with pretty extreme loading. So here, our live load is 3 to 5 kPa. Now, how often do you think in this region here you would ever get 5 people crammed into every square metre? Do you think that would actually ever happen in the life of this structure? You never know. So we have to assume that's the case, and for strength, we multiply that by 1.5. So when we're doing our ultimate limit state check, We multiply that by 1.5. So we reduce that up to, if we're talking with 5 kPa, we actually design it for 7.5 kPa because you never know in terms of life. In terms of deflection, what do? We get our 5 kPa and we multiply it by 0.7. And that reduces it to 3.5 kPa. Which, do you think you'd ever get 3 people per square metre up here? You may. If that is exceeded, will the building fall down? What's going to happen? Well, if this wasn't a ground floor, what's going to happen is maybe the ceiling below me might crack a bit. Yeah? So it's not a catastrophic failure that we're talking about. So that's why we put smaller load factors when we're designing for deflection. Now, if you've got that many people crammed in here, do you think they'll notice that the floor's deflecting a little bit more than it would otherwise be deflecting? No, they're probably worried more about someone putting their hand on their bum than anything else. So can you see that's why we put different load factors for these two situations. When it comes to strength, for failure, we increase our load dramatically. When it comes to deflection, we treat it as at a reasonable. We have a lower level of loading on there because the consequence of failure is not catastrophic. Something might crack. A pipe might burst. So, in summary, dead load, self-weight, permanent fixtures, live load is the removal part of the load. All unfactors loads, assume them to be characteristic loads. That's loads that have a 5% chance of being exceeded. So if you're given a group of numbers, you can work out the mean and the standard deviation to work out what your characteristic load is. And as I said, you'll be doing that next week in the practice class. We apply the load factors to the characteristic loads to increase safety, and we use limit state design. So primarily things are designed for ultimate and serviceability limit state. One is designed against collapse, one is designed against excessive deflection. One has the bigger load, one has the smaller load. Now at this point here, people say to me, but hang on a minute, Lizzie, this case is never going to be critical here because the loads are a lot smaller. What you will realise when you work through the procedure is when we say we have two different designs, we actually do two different checks on them. This one here, we check our stresses are less than the allowable stress. Over for serviceability limit state, we actually physically calculate how much something deflects, and we ensure it's less than a maximum deflection here. So there are two independent checks we do, two completely separate independent checks. And if something is within the range of both, our building is acceptable. If you say, no, the beam deflects too much, then you have to put a bigger beam in, bigger than is required for strength. Or no, it's going to fail, but it's not deflecting too much. You still have to put a bigger beam in, and it'll deflect even less. So these are two independent checks you do, and you'll be doing that with your third project. Okay, so we're going to do some worked examples now. We're going to actually do some calculations. Before we do, quite often you'll see beam designations. The standard steel beam is a universal beam. If you're parked in the car park, engineering car park, all the beams in there are UBs. So when you're given a UB designation, the first number represents the depth of the beam. So if you had a 310 UB 40, that's telling you it's a universal beam. That's telling you it's 310 millimetres deep. And the 40 is telling you it weighs 40 kilograms per metre. So that building friend of yours that asked you to lift those precast panels has run you up again. I've got a couple of UBs I need to move. Ask him what the designation of them is. If it's a 510 UB 100, it means it weighs 100 kilos per metre. Again, sorry, I'm busy. I can't help you that day. If they're small beams, okay, and they weigh 15 kilograms per metre, so if it's a 210 UB 15, they're lighter weight. Okay, let's do a problem. This is taken off a very old exam paper, but will give you some idea of the type of exam questions we have. Now, what I can do here, I'm just going to try some new room tech. I'm going to freeze. All right. Okay, and then I'm going to give myself... Oh no, that didn't work, did it? Hang on, let me try that again. Freeze. All right. Actually, I don't want to freeze the right because that's the side being recorded. I want to unfreeze it and I want to freeze the left. I'll get this right in the end. Choose to display freeze on the right. No, there's no option for left. We could freeze the right and all the people that have decided not to come to the lecture will just miss out. Oh, but I won't be that mean in the first week. Will I be that mean in the first week? Oh, you are mean. No, I can't. I better not, because you know what? Then people email me and complain. So we can't freeze it. Oh, I was looking forward to using that feature. Okay, let's go back to the question where you can read it bigger now. We have a concrete slab. It's 300 mil thick. If you look at the diagram, you have to start being able to understand and read information like this. It's 5 metres wide and it's 9 metres long. It's used to support a live load of 4 kPa, kilonewtons per metre squared. I'm going to be saying kPa because kilonewtons per metre squared is too much of a mouthful. The concrete slab is supported by 2 brick walls. Well, they're hardly walls, but 2 upstands, 200 mil by 500 mil by 9 metres long. If you look at the diagram here, you'll see it's 500 mil high and 200 mil wide. And that, in turn, is supported by a steel beam under here. Given the density of concrete, 24, the density of brickwork, 19, and the weight of the steel beam, so they've told us how much the beam weighs, calculate the dead load and the live load on each steel beam in kilonewtons per metre. Okay? And then it says calculate the ultimate limit state design load. So you're going to calculate a load up here, we'll call it W, kilonewton per metre. And when you calculate the ultimate, you're going to calculate a dead load component and a W live load component. And then when you come here to calculate your ultimate limit state, that will be 1.2 times your dead load component plus 1.5 times your live load component. And that will be your ultimate limit state load. And that's on the basis that you now have a beam 9 metres long and it now carries a load W alt. So that is then your starting point to check the stresses. Once you have your load on your beam, you go, okay, we can now start working out what the bending stresses are on this beam because it's bending. So you have to turn your loading, your weight, your real life loading into an idealised number. So we clear where we're at now? Okay, so let's get going. And just to repeat again, these inkings, I'm a bit messy. I just can't neaten up my writing. I'm sorry. I'll try and make it neater. I will usually put them online. There's a little folder in the lecture area. I'm not sure if it's hidden or you can see it yet, and it's empty, called Lizzie's Inkings, lecture inkings. And then what I'll do is I'll get these PowerPoints and I'll take everything else out except the slides that I've written on, and I'll put them in there. So by all means copy them down, okay? But be aware that they're there as well if you think you've copied down something incorrectly. And also these lectures are being recorded as well if you choose to hear the whole thing again. Okay, so we want to calculate the weight. First of all, what's the question? Calculate the dead load and live load on each steel beam. Now the first thing you have to be aware is it says the weight on the steel beam. This actually includes the weight of the steel beam. So always include all the loading, all the self-weight loading. Before something can carry more load, it has to be able to carry its own self-weight. So our dead load here, often called G, will be equal to the weight of the steel plus the weight of the bricks plus the weight of the slab. And we're trying to calculate that in kilonewtons per metre. So looking at our steel weight first, in kilonewtons per metre. We've been told it weighs, over here, 60 kilograms per metre. So we already know how much our beam weighs. We don't have to do anything to it apart from convert to kilonewtons per metre. So we get our 60 kilograms per metre. We multiply by 10 to convert to newtons, and then we divide by 1,000. So that will give us the weight here as 0.6 kilonewtons per metre, and that's for the steel. Oh, no. Oh, hang on, I haven't got it on pen, have I? Pen. Now, and now it's not red. The bricks now. I want another colour. Fussy. Give me a blue. Okay, our brickwork now. Our bricks work weighs, we were given the density as 19 kilonewton per metre cubed. So I'll do it the long way now. We need to know the volume. Now remember, we want to know the load, be clear, on each steel beam. So we're going to work out the weight of the bricks on one steel beam. So the volume of our brickwork is 0.5 times 0.2 times 9 metres long. And that now, when I multiply out, will give me a load in kilonewtons. And I want it in kilonewtons per metre, so I'm just going to divide by 9 there. And that will give me a load of 1.9 kilonewton per metre. Now can you see here that I've divided by 9 and multiplied by 9 here? So the other way to have looked at this was to say 19 times the cross-sectional area, and that would have just been 19 times that little cross-sectional area there, which is just your 0.2 times your 0.5. So it's one extra step. If you need to do it, I don't have a problem with it, okay? Okay, then finally, we have the slab weight. So we want to know the weight of the slab on one beam. So we want to know half. So if you were doing it the quick way now, you would, in terms of cross-sectional area, just look at the cross-sectional area of half of the slab. So here, and it keeps on changing the colour when I jump slides. So you could say, well, our density here is 24 kilonewtons per metre cubed multiplied by our cross-sectional area. And that's equal to 24 times our width here was 5 metres. So that's 2.5 metres. And our thickness was 300 mil times 300. And that will give me a load of 18 kilonewtons per metre. The other way to do this is to say 24 kilonewtons per metre cubed times the volume, and we'll say the total volume, divide by 2 beams, divide by 9 metres. So that would be an alternative way to do it. And doing it that way, you will get the same answer. So doing it this way, you would get 24 times the volume of our slab is 5 times 9 times 0.3. So that's our total volume. Then we would divide by 2 beams and then 9 metres, and that would also give us a load of 18 kilonewtons per metre. So, if I could freeze, let's just freeze the right one for the time being. Oops. Okay, so you can see our loads there. So our total dead load now is equal to our 0.6 for our steel plus our 1.9, and I should put units in here. Total dead load in kilonewtons per metre on one beam. Always tell yourself, remind yourself what it is you're trying to calculate. That's the brickwork plus 18 kilonewtons per metre. That's the slab. And that gives you a dead load of 20.5 kilonewtons per metre. Does that make sense? Can you see where I pulled everything from? Okay, now I will unfreeze for the people that aren't here. Then we need the total live load in kilonewtons per metre on one beam. So our live load, you can't see this, but to remind you, was 4 kilonewtons per metre squared. And we want our live load on one beam. So the quick way, 4 kilonewtons per metre squared times the breadth or the width over which the live load acts. And what is that width, everyone? 2.5 metres. So it's simply 8 times 2.5, which is 10 kilonewtons per metre. Now again, alternatively, and I don't mind how you do it, and I can't reiterate that enough, I have 4 kilonewtons per metre squared. I'm going to multiply it by the entire area, 9 times 5. Now that's given me a load in kilonewtons on the whole thing. I have 2 beams, so I'm going to divide by 2 beams, but that's still a load in kilonewtons, so I then have to divide by the 9 metres. And that will give me the same answer, 10 kilonewtons per metre. So finally, our ultimate limit state loading in kilonewtons per metre on, rather than get the eraser, I'll just, on one beam. This is our final answer. Well, that's equal to 1.2 times our dead load of 20.5 plus 1.5 times our live load of 10, which is a value of 39.6 kilonewtons per metre. And that now is the starting point. That's this load here, WAlt, for our 9 metre long beam. That's the starting point for the analysis. Any questions with that? Come after if you have any questions with that. Okay, bit of light relief. When I was in Newcastle seeing the Angel of the North, of course you have to go into Newcastle itself. It's a lovely town. And the Tyne River passes through Newcastle, and within a 1 kilometre stretch there are 5 bridges. So if you like your bridges, it's a good place to go and see your bridges. You can see them down here. You can see the Sydney Harbour Bridge here, and you can see a lower bridge in red here, and to let boats through, this lower bridge in red rotates on a vertical axis, opens up, and then you have this arch beam bridge up here that's a lot higher so the boats can get under. And this Gateshead Millennium Footbridge was completed in 2000 as part of the Millennium celebrations, and it's low. and they had to allow boat traffic through. So it is the world's only tilting bridge. So what it does is it tilts up on these pivot points down here. It operates like the lid of a giant eye, slowly opening and forming an arch under which the ships pass. So of course the architects had a great time designing that. Took it to the engineers, and the engineers said, yeah, we can make it work. So what did you hear? It is part arch, part suspension, and this deck in here, well, it's beams in between the suspension. Because there's a curve in it, there's also torsion and twisting forces occurring. So this would have been analysed using complex modelling on a computer, by a computer, not something that could be done by hand very easily. So the bridge itself, I think, is quite delightful, but interesting is how it was constructed. So on both sides of the river, you can see a lot of structure, so there wasn't much room to build this thing. So what they did was they carried the completed structure upstream by using the world's second largest floating crane, which has a deck the size of a football pitch. So they shipped it up there, and then they would have had a crane here or on the actual barge, and then they would have lifted it into place. They would have built the fixing here, the pin connection here, soldered it in, stuck this pin in here in on both sides, and there's your bridge. I don't think it would have been that easy, but there's your bridge. So this bridge here rotates. It takes 4.5 minutes to rotate from 40 degrees from the closed to the open position. And it just uses some simple hydraulic rams in here, powered by a 55 kilowatt motor. So not a lot in there. So that's the Gateshead Millennium Footbridge, which I think is a lovely structure and more unusual because of the way it tilts open and closed. So if you're ever in Newcastle, go and have a look. And if you ever want to design something like that, you've got to know how to design a timber plank on a steel beam. So this is the second and will be the last example. So would you like a 5-minute break? Okay. Have yourself a 5-minute break.